Okay, so in this part, we now want to work out a question where we're looking at a box that is to be made from a 12 meters squared piece of cardboard. Now, we want to make sure that the volume of this box is maximum. Well, they've been given us the dimensions here. All we know is that if we're finding the volume of a box, we have to multiply the dimensions. If let's say we have X to represent some piece, Y to represent some dimension, and Z to represent some dimension, we know to say the volume of such a box is going to be X multiplying Y multiplying Z. So this is how we're going to get it. But let's establish the methods that we want to use to work out such a question. Well, in an event that you're trying to find a maxima in a certain expression, but you're being controlled by a certain parameter, that parameter which is controlling you is what we are calling the, what's that? We're going to call this the constraint. So here we're being controlled by the 12 there. So the 12 becomes our constraint. Now, what does that imply? It means that whatever we do, we have to be limited by whatever that constraint, whatever that condition is going to be. Well, it turns out that in such cases where we have one or two constraints in place, the same methods we used earlier in terms of determining the maxima or minima can be used. But now we just want to factor in what the constraint is going to, or what the constraint is doing. Previously, we sought to say, if we have a function f, a function of x, y, and z, and then somehow we write this as equals to 0, and yeah, basically, even if we just write, we have function f of x, y, z, and then we wanted to maybe find the maxima, the extreme points of this function. We had to get the partials at a specific point, or the partial of this, a function of x, y, z, equate to 0, then get partial also equate to 0, and also get partial z and also equate to 0. So the partials had to be equals to 0 respectively. But now we have a constraint in place. What does the constraint do, and how does it change our approach? Well, all we're saying here is that for such expressions, it so happens that if we wanted to find these extreme points, we just have to make a slight adjustment to our expressions. Let's say we have an expression, a function of two variables, x and y, and this expression, we want to find its extreme points. Well, all we're saying here, and let's say it's subject to a constraint, let's call that constraint phi. And phi here is also a function of x and y. Now, how do we deal with this? Well, in this case, to find these extreme points, it's a similar structure, but now we're just going to bring in what that constraint is. First, get the partial x of your function. Now, instead of just equating it to 0, you now have to bring in that constraint. But to that constraint also, get its partial with respect to x. So if f here is being evaluated with respect to x, even the constraint differentiated with respect to x, it's partial with respect to x. And then, of course, this is a function of x and y. The only difference is the constraint here, you have to multiply it by a constant lambda. And this constraint is what we are calling the Lagrange multiplier. So lambda there is going to be the Lagrange multiplier. Of course, the owners of the word will pronounce this in a different way, but let me apologize if the owner of the language gets to watch this. So yeah, Lagrange multiplier. I have to Google how you pronounce this word. Okay, so this is what the lambda there is. So sometimes they'll specify that find the extreme point and also maybe find what the multiplier lambda is, but sometimes maybe you just find what the maximum is going to be, or the maximum or minima is going to be. In that case, you might not need to find the multiplier, but it's going to be one of the things that show up in your calculations. Now, of course, to work it out for y, we are also going to do partial f, partial y, plus, also you have the same multiplier. And then you have, but now the constraint with respect to y also equals to 0. But for this expression, notice that you now have three unknowns: the x-coordinate of that extreme point, the y-coordinate of the extreme point. The third constraint, the third unknown is going to be the multiplier lambda. Now, you know to say when you have three unknowns, it implies that you need three equations, at least three, to work out the problem. The third equation here is going to be that the equation of the constraint is, before it is even differentiated, this is a function of x and y. This equation on its own must also be equals to 0. So now you have the third equation. These equations can now be worked out to find out what x, y, and what that constraint is going to be. So this is how you evaluate this. So you just need the equation of exactly what is happening there, the equation whose extreme points you're trying to determine, then the constraint that is controlling, or the condition that is manipulating that equation, or that is helping you determine what the extreme is. Then after that, the rest can be done using these formulas. Let's go back to the question that we had earlier, and let's see how we can solve it using the method that we have just described here. The difference here is, unlike my description, which was only x and y, this one now it's a box which has both the x-axis, the y, and the z-axis. First, let's start by creating a picture of how our box is going to look like. So we have something like this. Does this look like a box? Okay, that looks okay. Then we'll just copy this. Okay, so let's take this to be our box. And of course, don't make a mistake of assuming that this is a cube. By cube, we're now saying that the sides are equal, as in all the sides, the lengths are going to be equal. This is a box, meaning that we can say this is x here, we can say this is y here, and we can take the height here to be z, but they are not necessarily the same. I am not saying that they are not the same, but I'm saying they might be the same, but only calculations here will confirm that they are or they are not. All we want is what they have to be if the volume is to be a maximum. But the only condition is we are making this box from a piece, more like a sheet of material, and this sheet of material, it has a total area of 12 meters squared. Notice that 12 meters squared, it's the area of the materials we are supposed to use to make that box. You have to understand that. Meaning that when we cut this into strips, we're assuming that nothing is being wasted. All the pieces, or all that 12 meters squared, is being used. So when you cut this into pieces, you're going to make this face here. But you know you have to make this face twice because its relative is going to be the other side. You also have to make another face. Let me go blue. You have to make another similar to what I already have there. Or I can go blue, but I just have to go white with these. Okay, so this part here, it will have its own area as well, but it has to be made twice because it has to match this. It's the same piece that side. This yellow one as well, it's made twice. One piece is this side, the other piece is that side. But you have to see that only one piece is made once, and that is the base. Why am I saying that? Because the question specifies, let me leave this open because it looks like it's disturbing what is happening on top. But we know to say this is basically the same as this front part here. But the top part is to be left open. Why? Because the question specifies that we are making a box that doesn't have a lid. So meaning that the bottom part there is, we will have a piece for the base, but the top is going to be open. Now, what does this imply? It implies that the total surface area, which will have the area of this yellow piece here, area 1, the area of this piece here, area 2, the area of the bottom there, area 3, the bottom, the one at the bottommost point, plus their relatives. In other words, by relatives, I mean the ones which are equal to them. The total surface area has to add up to 12. But how do I get that total surface area? It's going to be area 1 here. And for area 1, notice that I have to multiply x times z. It's basically going to be this length times the z, the vertical one, which is this one here. So it's x times z. But this surface occurs twice, here and its relative here, the counterpart there. So because it occurs twice, I have to put 2xz so that I account for the other one as well. Then plus, now I come to the one being made by y and z. So the area there is going to be yz. Again, this surface here is being made twice, this side and this side here. So I will put a 2 here. I have 2yz. The last one is the one down, the one at the base. The one at the base only occurs once. The top part is to be left open. The question specifies. So the one at the base is just going to be x, y. So I hope that part is clear. So this becomes the expression for our surface area. And what is the question saying? If you recall, the question did specify that the total surface area is subject to this condition, that it has to be equals to 12, because that is the maximum material that we have. So in other words, if we get 2xz plus 2yz plus xy, this has to be equals to 12 meters squared. So as the equation for our constraint, if I label this as phi, notice that this is a function of x, y, and z. Remember, phi has to be equals to 0. So when I write this, I'll have this as 2xz plus 2yz plus xy. The 12 will come to the left, and this will be minus 12, so that this is equals to 0. This becomes the constraint. Now, the constraint for what? What are we controlling here? Let's get our original function f, also a function of x, y, and z. Now, this is a function for the volume. For the volume, that's the one which we're trying to find big maximum, which is the maximum here. In this case, we are dealing with the volume of our box can be by multiplying x, y, and z. This is going to give us the volume of the box. So it's x times y times z. So these become the two expressions that you have to play with. At this point now, it should be straightforward what you have to do. You have to get the partials. Remember how it goes? Get partial x of that function, and then plus the condition or the multiplier, and then this multiplies the partial derivative of the constraint, and then this is also a function of x, y, and z. Then this equates to 0. This becomes the first equation. And then also you have partial y, partial f, partial y, x comma y comma z. Then you have plus the multiplier, the constraint differentiated with respect to y. Then you have x, y, z equals to 0. In the same way, you have fz here, x, y, z, plus this partial z, the x, y, z equals to 0. Then lastly, 3 equations. But look at the number of unknowns you're going to have here. X, y, z would be 3 unknowns. Then the Lagrange multiplier would be the 4th unknown. So you need at least 4 equations. The fourth equation will be the one for the constraint, which is x, y, z. This also has to be equals to 0. So these are the four equations that you will have to solve in order to figure out what is happening here. Any questions so far? Okay. So partial derivatives. First, let's get partial f, partial x. Partial f, partial x is basically just this. With respect to x, we're going to have yz. Partial f, I can actually just go right ahead and write what we have there. So for the first part, what we have is going to be yz, and then we have minus. This is going to be lambda, and then we have the partial derivative of our constraint. Constraint is this one. With respect to x, we're going to have x here, and then what else? 2x, 2x, not 2x, 2z. And then this part is going to be 0. This part is going to be plus y. The rest is going to be 0. So you're going to have just 2y plus z. So this is going to be this, then 2y z. Not 2y plus z, 2z plus y is equals to 0. So this is what we have here. So we have yz is equals to negative, then we have lambda 2z plus y, just like this. What else do we have? Well, we can do the same thing for the others. Let's now get partial f, partial, where's that? Partial f, partial y. Partial f, partial y is going to be xz or zx. So basically, we're going to have xz minus, plus, lambda. And then the expression here for the constraint, this is what we have. With respect to x, this is a 0. To y, this is the first part is a 0. So we're going to have just 2z here. And then to y, this is just going to be plus x. So 2z plus x. So we have 2z plus x is equals to 0. So that we have xz is equals to minus lambda 2z plus x. So this was our first one. Then we do the same thing for the others. You should see that the next one is going to come out as xy is equal to minus lambda 2y plus, what do I have there? Not 2y. Yeah, this is going to be 2y plus 2x. The fourth one, is going to be xy. Basically, this is going to be the third one. I think this is partial z. Partial z will come out like this. But then we have that last one where we are equating the constraint to 0. So the constraint itself, where is the constraint? This is the one. So just getting this, it's already equated to 0. So I can just copy it from here and bring it here. So this is what we have for number 4. So we have our 4 equations and we have 4 unknowns. So you should be able to solve these equations to find what x, y, z, what they are. Now, how do we do it? Well, there are a number of ways that you can do it. Let me just get the other equations so that I bring them all. So these are equations here. Okay. Now, how do we solve our equations? So again, it's up to you how you want to work them out. among the methods that you can use here, to make them similar, just look at how best you can work them out. Look at equation 1 and equation 2 here. You see, you can multiply x to both sides of equation 1. And you not say that's not changing anything, because multiplying by x is basically just, since you're doing it both sides, just multiplying by 1. So let me get this. I first want to work out these two together, equation 2 and equation 1. I want to combine them. So if I am going to combine 1 and 2, what will I have to do? So in this case, I have to multiply both 1 and not just 1 and 2. I'll just multiply 1 by x. So what will happen when I multiply 1 by x? So if I multiply equation 1 by x, look at what will happen to it. It will mean that the left side will become x, y, z. What else? And then the right side will now be minus lambda. The x can be sent inside directly, so that now I have 2xz plus xy. This becomes equation 1 when I multiply it by x throughout. Now, next up, I'll multiply equation 2. Can you guess what I'll multiply equation 2 by? I want it to be similar. I'm using that method, by y. I'm using that method of solving simultaneous equation, elimination, if you guys remember. So when I multiply by y this time, look at what happens to equation 2. This becomes x, y, z, the left side. And this becomes minus y. This becomes, let me just rearrange. When I rearrange, this is going to be 2x, there's not 2 there. This is just going to be xy. And then plus 2yz. 2yz, yes. 2yz. Okay, so this is now what I have from equation 2. So when I write them together now, so that you compare how they look like, you should see that these equations are similar. They can easily be combined. This is how they look like now. This being 1 and this being 2. Now we can subtract them. If you subtract these two equations, again, doesn't matter which one you subtract from what, still going to give you the same results. So when I subtract them here, I'll say from 2, I'll subtract 1. The left side will be 0, and this becomes minus y, lambda I mean, and then this is going to be x, y, plus 2yz, and then this is going to be plus lambda, and then 2xz plus xy. I don't even know why I switched that part. Should be okay. You see that lambda here falls off. Lambda is going to cancel out. Or instead of canceling out, we can say that among our options, we're going to have the part where we're saying 0 is equal to, factor out lambda, or I can basically, let's distribute first, so that you see how it simplifies a little. Lambda x, y, minus 2 lambda yz plus 2 lambda xz plus lambda xy. This and this will subtract out. They'll give us 0. So if I rearrange now, I have 2 lambda xz minus, is there a minus? Yes. 2 lambda yz is equals to 0. Well, 2 cannot be equals to 0, so 2 is out here. Then when we factor out this, I can keep the 2 there, but 2 is basically out of this. We now have xz minus yz is equals to 0. Or even the z can be pulled out, x minus y is equals to 0. What does this imply? It implies that either lambda is equals to 0 or z is equals to 0 or x minus y is equals to 0. These are the three possibilities. But clearly, z cannot be 0. Why? Because then what kind of box do we have with if the height is going to be 0? So clearly we can't have this one. Z is equals to 0 is out. So I hope that part is okay. And if we try to insert lambda into equation 1, let's see. Let's try. You have to see that lambda there will also fail to work. But where are we going to plug it for us to see that it fails to work? If we bring lambda and plug it into our equations 1, 2, and 3, notice that it will mean that this part is 0, this part is also 0, and this part is 0. So that it will now mean that this is equals to this, which is equals to this. And what would that be equal to? They will all be equals to 0 because the right-hand side of each term is now 0. But that cannot work as well, because we must have the perimeter or the total surface area to be 0. Because notice that the left-hand side here, they are actually just giving the surface area of the sides. What do I mean of the sides? Notice that what we have here, that is YZ, and the other one is ZX, and the other one is XY. And we know to say, if I just double this, added it to double this one as well, then added it to 1 time of this because the top is open, we should get 12. But if they are 0, I have 0 here, and this is 0, and this is 0, that is not equals to 12, implying that we can't have lambda being equals to 0, because it won't give us a total surface area of 12. Because of that, we can't have lambda being equals to 0. Because lambda cannot be equals to 0, the only possible continuation is the last equation. And from the last equation, what do we have? We have this. But before we proceed to that, do we have any questions based on where we are up to now?
What did you say before?
Before what?
Maybe your last 10 words.
Okay, so I was saying that we cannot have lambda is equals to 0. Why? Because if lambda is equals to 0, it will imply that the three equations, these equations here, equation 1, 2, and 3. From equation 1, 2, and 3, it will mean that lambda here is 0, meaning y times z has to be equals to 0. X times z will also have to be equals to 0 from equation 2. And x times y will also have to be equals to 0 from equation 3. But that cannot be so. Why? Because if we try to calculate the total surface area of our shape, remember the constraint, it's xz time 2 times xz, 2 times yz, plus 2 plus just xy must be equals to 12, this one here. But if this is 0 here, and this is 0 here, and this is 0, then we cannot have this being equals to 12. It fails to give us that 12. So when lambda is said to be 0, then that constraint will not be satisfied, or that condition will not be satisfied. Therefore, we cannot have lambda being equals to 0. It's limited, it's restricted by that condition. Are we okay now? Are we okay? Okay. So based on that, the three solutions we found were they? After solving our equations, or just from equation 1 and 2, we ended up with three possibilities. Lambda is equals to 0, z is equals to 0, or x minus y is equals to 0. We've just eliminated the first two possibilities, meaning only the third one has survived. But does the third one make sense? Let's try. From the third one, we have x minus y has to be equals to 0. But will it work? See, this means that x is actually equals to y. Now let's substitute this into equation 3. Remember, we started with equation 1 and 2 to come up with this. So let's plug it into equation 3. From equation 3, what do we have? Equation 3 is this one. So when we plug in that value or that statement that x is equals to y into equation 3, what do we end up with? You see, if x is equals to y, putting it into equation 3, where there's y, we'll put x. So this becomes x squared here. This now becomes equal to minus lambda. And then we have, this is going to be 2, and then this is going to be x plus 2x. So this is now leading us into x squared is equals to lambda. And then we have, So yeah, let me just repeat that just in case. So here, of course, we're going to have a problem with that minus, because this is going to end up being minus 4, and then this is going to be lambda x. So this is literally what you're going to have here. But can we work around that? I think we can do that. I think we can do that. You see, in this case, once we reach this part, if we wanted to work this one out without having to get rid of that negative, how would we do it? Just move this to the left side so that now you have x squared plus 4 lambda x is equals to 0, so that you have x here coming out. Then you have x plus 4 lambda being equals to 0, so that you have either x is equals to 0 or x, I hope I haven't made x, yeah, lambda is equals to 0 or x plus 4 lambda is equals to 0, implying that the second term here has to be this is equal to negative 4 lambda. Is that okay? Found a work around that. Okay, so this becomes what we have for our lambda, for our x, I mean. X is equals to minus 4 lambda, and then the other term there, that's x is equals to 0. Again, x cannot be equals to 0, and the problem there is that if x is 0, then what type of box do we have here? So we have to play with x is equals to minus 4 lambda. You see, what this is going to do, because I have this negative here, it will imply that perhaps that negative has to be part of the lambda and not the dimension of the 4, because we need the 4 to be positive if we are really making for this to be a box. You don't need the box to have negative dimension there. It just has to be a scalar, its dimension. So we can just treat this as 4 lambda, or you can just take the negative to be part of the constant and not the dimension. But let's see how we proceed. We'll keep the negative there for now. But in case we find the final answer, we're just going to leave it out, and the dimensions are going to be taken as positives. Okay. Now, once we have x figured out there, now what we have to do is we have to plug in x is equals to negative 4 lambda into equation 1. So let's get equation 1. So equation 1, where is it? This is what we have somewhere. Let's see. Equation 1, we have this. So we'll plug in x into equation 2, and what do we see? So into equation 2, when we plug in x, what we're going to have is going to be minus 4 lambda z equals to minus lambda, and then this is going to be 2z, and then this is going to be minus here, and then we'll have 4 lambda. If we continue with this, we see that this is going to be minus 4 lambda z is equals to, I'll distribute now, but notice that the negative can cancel out from both sides. If the negative falls off, we now remain with 4 lambda z is equals to 2 lambda z. This will be minus 4 lambda squared. At this point, lambda can cancel once because we're just trying to simplify this anyway. Or I can say this goes to the left, the other one goes to the right. We end up with 4 lambda squared. On the right side, we're going to have 2 lambda z minus 4 lambda z. So this is going to be equal to, when you simplify this is going to be minus 2 lambda z, and this is 4 lambda squared. So you see that lambda can cancel once, so that we now have 4 is equals to 2 minus 2z. So here, this was, we're seeing that error I talked about earlier, that negative that we kept. Now we're seeing the dimension coming out as negative, z is equals to negative 2. So in this case, of course, if you want to avoid this, all that you'd have to do is, when setting up these equations here, you can take this part here to be negative, so that when they go to the right side, there'll be positives. But everything else, the treatment is the same, and you'll still find the exact solutions. But the difference is that now we are going to have positive z instead. So if you do this approach, the desert dimension, because this is a scalar, you have to take it as only positive 2. It's not just positive 2 like that. We still have this 1 lambda remaining here. So this is going to be minus 2 lambda. So keep playing with the negative here in this case because we kept it. But in giving the final answers for that maximum, I only have there the positives then. So z comes out as minus 2 lambda. Once we have that, what comes next? Okay, so since we have x is equals to minus 4 lambda and z is equals to minus 2 lambda, what happens next? Now we have to figure out what y is. So let's go back to our equations. To figure out y, what we need. So just look at your equations somewhere here. Which one can we use to find what y is? We have z, we have x. You can use either the first one or the third one. So either the first one or the third one will work. So let's get the third one. So in the third equation, where there's x, we'll substitute what x is. That minus 4 lambda. So what are we going to get there? So now we have minus 4 lambda y is equals to minus lambda, then 2y, then we have plus, this becomes minus. I see x there, so let's say plus, it's going to be 4 lambda minus, of course. Is that correct? Let's see, minus 4 lambda, yes. Minus minus goes, we have 4 lambda y. Lambda, I can say lambda cancels here, so that I have 4y is equals to 2y minus 8 lambda. Okay, so yeah, this is what I have. The 2 goes to the left. I now have 2y is equals to minus 8 lambda, so that y is equals to minus 4 lambda. We're now seeing that x is equals to y, and in this case, we're getting minus 4 lambda. So this is what x and y. So x is minus 4 lambda, y is minus 4 lambda as well. Z came out as minus 2 lambda. Now to find something here, to find anything now, we're going to turn to the fourth equation because it's the only one that we haven't messed around with. Where is the fourth equation, which is this? We're going to substitute what x is, y is, and z so that we get what lambda is. So go to equation 4. And in equation 4, where there's x, we'll put minus 4 lambda. Where there's z, we'll put minus 2 lambda. Then plus, we have 2. Where there's y, we have minus 4 lambda, because y is also minus 4. Z minus 2 lambda. Then we have xy there, so this is plus x minus 4 lambda, y minus 4 lambda as well. Then minus 12 is equals to 0. So now we have substituted everything. All we have to do is now simplify. When we multiply these, this is going to be plus 2 and 2, 4, 4 and 4, 16, 16 lambda squared. This becomes plus 2 and 2, 4, 4 and 4, 16 as well. So we have 16 lambda squared again. Okay, so let's continue. Then we have plus, this is 4 and 4. Again, we're seeing 16 coming out there. So we have plus 16 lambda squared. Then we have minus 12 here is equals to 0. Okay, so any questions so far? We can try to simplify this. These are all lambda squared. Looks like, let's see where this goes. Let's take the 12 to the right side. We end up with 16. 16 adds 3 times. So at 16 by 16, 32. 32 by that, we get 48. So we now have 48 lambda squared. This is equal to 12. And we get lambda squared is equals to 12 divided by 48. So that lambda will be equal to 12 over 48 is that 1 over 4. So we now square root this. We know the square root is either positive or negative. So that when we simplify this, lambda is equals to plus or minus 1 over 2. Now here we have found what lambda is, 1 over 2, but either positive or negative. Now comes that condition. These are dimensions and they are scalar dimensions. We must have x to be greater than 0. We must have y to be greater than 0. And we must have z to be greater than 0. So regardless of what we have there, our approach was to take that sign on the middle to be positive, and we ended up with x being equals to negative 4 lambda and z being equals to negative 2 lambda. But we must have z as a positive number. What does that imply? It then implies that we must pick a choice of lambda that ensures that these are satisfied. What do I mean? You see, x is equals to minus 4 lambda. If lambda is positive half, if lambda is equals to minus 1, let's say plus 1 over 2, it implies that x will be equals to minus 4 and then 1 over 2. X will be equals to negative 2. But we don't want to have a negative dimension here. They must be greater than 0. Because of that, we are going to go, we're going to go with lambda equal to negative half. Remember, lambda is equals to plus or minus half. When we go with lambda is equals to minus half, what do we end up with? We now have x is equals to minus 4 minus half, which correctly gives us x as 2. Now we are happy. In the same way, for lambda is equals to minus half, y will come out as positive 2. And finally, for lambda also equals to minus half, z, which was minus 2 lambda, and now be minus 2, and then minus half, z will have to be equals to 1. So in other words, the dimensions that ensure that we are dealing with maximum is x is equals to 2, y is equals to 2, and z is equals to 1. What does this mean? It now means that the maximum volume, remember they wanted the maximum volume that we can have. The maximum volume will have to be f of 2, 2, 1. This will be Remember, the volume is X, Y, Z. So it will have to be 2 times 2 times 1, which will be equals to 4 meter cubic. That is the maximum volume that we can have there. This was long, but it was fun. What do you guys think? How was it? Any questions?